Kanika Narang is a research scientist at Meta Reality Labs, where she works on groundbreaking conversational AI projects for augmented reality, AR devices. And with over a decade of experience in AI, Kanika specializes in building models that solve complex problems like content safety and user behavior modeling. And she earned her PhD from the University of Illinois, Urbana-Champaign, and has published around 20 research papers at top AI machine learning conferences. And Kanika is a regular speaker and a panelist at global conferences, bringing deep expertise to the stage today. And again, please welcome Kanika.
Thank you so much. And good afternoon, everyone. Hopefully everybody had a good lunch. I am going to present my work on on-device LLMs. This was done with my colleagues at Meta, and we also published a paper if you're interested in looking at more details on what I'm going to present today. This talk will, this is the basic agenda. I'll just go through why do we need on-device or small language models, what are the techniques to train these models and related work in that space, and then I'll follow it up with introducing the methodology which we proposed, and then finally I ended up with our experiments, results, and some future work. So first of all, I think this is very virtual assistants in general are everywhere. This has become so clear in the last, I guess, 2 years. We see them in travel to give people more personalized recommendations and even do automated booking systems, even as a coding assistants for software engineers like all of you here. Even for healthcare now, they are improving diagnostics and bringing more personalized patient care. Most of these applications generally work on server-side infrastructure where you interact with these assistants through a device, typically your phone or a browser on your laptop. But all the processing, all the data transfer actually happens on the server. But imagine a world where we can host these models on your device, on your phone, for example. And that would bring a lot of benefits. First of all, the privacy. I guess a lot of discussion has been come up around the privacy protection on these models. So having applications which only can access the data which is private to users, for example, your phones or your financial transactions, and having that sent on the device without sending it to server, I think that would bring a big change in the applications which could be used using those LLMs. Also, because everything is going to be a smaller scale, it will be lower latency and therefore lower power and lower cost. But what's the problem? So why we're not building these small language models? So if you think of a model which can be hosted on the like a state-of-the-art smartphone you have these days, it's the best you can fit it into will be like a 1.5 billion parameters. That was what GPT-2 was. But the performance is a major concern. So if you see, like GPT-2 performed around 30% on this MMLU benchmark, whereas now with GPT-4, we have around more than 80%. So there's a big gap which these models need to fill. But on the other hand, we can use them specifically for a specific task as a task specialist. So how do we do that is we do fine-tune them on data sets which are specific for those tasks. So especially for devices or like wearables, creative tasks like you have like quick replying to messages or summarizing your documents or even instruct messaging. For those specific conversational tasks, these LLMs could be very useful. So but the reason, again, they're not useful for these even conversation, especially for longer turn, where you're talking to some for turns more than 7, for example. Their performance is not at all par. It actually declines steadily as you go into longer conversation. I don't know if you have tried talking with Alexa. It can answer perfectly one question, but yeah, if you ask it to refer to a previous context, I think the performance is really bad. So one of the reason for that is lack of good quality data. We do not have these data sets specifically, which are more generic, not very domain specific. And also one of the reasons is because it's very resource intensive to create these data sets. It's especially if you're asking humans to collect them, and given the size of these models, they need a lot big data sets. So again, it becomes a question of having those resources to create this. So as a solution, because we are working with smaller models, we have much bigger models which are really good at these tasks and can generate synthetic data, which could be used to train these models. However, we still have some requirements on how this data should be collected or created. So first and foremost, yeah, quality is the major concern. You need to make sure that they are not noisy. They are actually really good quality because you're using them in the later stages of training during fine-tuning. Then also they should be diverse enough. And third, they should be natural, because when humans tend to talk, they're using co-references to the previous context, they're doing topic switches, or they're rephrasing the text in more natural manner. So all of these requirements need to be met when we create those data sets. So to make sure that all of these requirements are met, we present our framework called CoDi, which is short on conversational distillation. This framework is able to synthesize these conversational style data sets on a large scale, make sure that they're diverse, and they're also steerable. This is how the framework looks like. So it's a little looks complicated, but it's very easy to understand. So we define a Markov chain or a graph where each link or each node here represents a turn. So essentially one Q&A pair. And you can go from one link to another with some probability. So this is what we define in the beginning. And then we sample this graph on based on how long do we want our conversations to be. So first, when you sample it, next, we execute each link sequentially. So what each link or each turn consists of is a prompt. It's a dynamic prompt where you can inject some dynamic hyperparameters. For example, I have given this hyperparameter of style. So for example, you want to create this this conversation or this Q&A in a layman term, like if you don't know about this topic, or it could be in a way that you are an expert and you're asking a question. So with these hyperparameters, you can tune in what style or in other parameters this question answer should be generated. And secondly, to make sure that these conversations are actually make sense, they follow a natural flow, we do also include linguistics phenomena like co-reference. So we prompt the model to make sure it's actually tied to the previous question. So overall, this is how the methodology looks like. You have a prompt template at each step where you put a context of all the previous turns, which the previous Q&A pairs, which the model has seen. And then you can also ground it in an external data. For example, you have a document corpus. As I said, like you have a set of messages in your inbox, and you want it to say summarize it. So that's one of the example we are looking at for grounding. So you feed this into a teacher model, which is we used a Llama 3 70 billion model, create a synthesized turn, add it to the context, and then repeat the process till you're out of all the turns. So this is an example of the data which was generated by our model. If you can see, so this is grounded in this document, which is about Vancouver and its population density. So it asks questions around like which cities are ahead of it. So it does use co-references and making sure that the questions are more diverse or also follow a pattern still. This was a qualitative example. On more quantitative side, we focused on the task of, again, grounded reasoning, where given a document, you have to generate Q&A pairs. Because we thought that scenario is ideal for the applications we're looking at. So for the model, we used the Llama 3 70 billion model as a teacher model, and then we used it to teach a student model of size 1.4b, which was based on Llama 2. For the experimentation data sets, we used two very popular conversational data sets, which are COQA and QUAC. So what they are is essentially they have some document corpus, and they have asked annotators to create Q&A pairs based on these documents. And also have divided these turns into train and test. So what they do is we haven't used the human created data sets, which they have, but used the documents itself and then generated Q&A pairs using our framework. And then finally, test it on the test set. This is how the results look like. To explain it further, so if you look at the in-domain section, what it means is, if you see the human singleton, that means we used the model, essentially the same LLM, but just trained it on the first turn. Whereas the human multi-turn is, we used all the multi-turned question-answer pairs and trained the Llama 2 model on that. And CoDi is the one which we trained on our generated data set. So if you can see carefully, there's a marked difference between if you just train it on first turn versus multi-turn, or even only on human data. But our model is able to get very close to it, the human performance. So that's kind of showing that we are at par in some sense to what the humans can generate. In the other part, which is the section which is the zero-shot setting, we did not give the model the conversation data sets, the conversation document, which we used in the first section. So they were trained on web data. Essentially, we got some documents from Wikipedia and generated Q&A pairs. So they were out of domain, not similar to what the test set was. And we see that instead of just using a general checkpoint, which is the instruction tune checkpoint here to represent, is doing much worse if you essentially than doing fine-tuning on using our data set. And we see that even at 1.4b scale and even at 7b scale. So again, that's kind of going to show that if you fine-tuning with good quality data actually outperforms just using the model out of the box. And even for 5.3, it's actually 5.3 mini, which is double the scale of double the parameter size, we are able to do at least similar to what they are doing, like a competitive performance to a much bigger model too. And finally, we show that also larger data sets also lead to a better model performance. So that's also very intuitive, but we did the analysis and we show that we do this is also out of domain. So even if we have a larger sample, but that's out of domain, we are able to see performance gains on some other domain data set. And it's important to note that it's cheaper or even much cheaper to create data sets of this scale, like 1 million question-answer pairs using a model versus actually employing humans to create the data set. And finally, we also see that the model performance actually outshines in longer turns. So in our experiments, we actually created multi-turns ranging from, I think, 5 or 7 up till 20 turns. So if you can see, after turn 7, there's a marked improvement in that red graph or the red line, which is our model, versus the ones which were trained on the human-annotated one. So showing that, yeah, good quality data, longer data turns does improve performance. Finally, we also expanded our framework to multimodal models. So here we replaced the language backbone of the model with the one which was fine-tuned on CoDi, using a CoDi data set. And then we did the alignment essentially with the vision model. We did not change the vision model. And the task, again, is grounded reasoning. So given an image, there are question answers based on that image, and the model is supposed to answer those questions. So again, I think we did see a much more improvement using our model, which is fine-tuned, than the instruction-tuned Llama model on both of these data sets. And it was surprising to see even like all these state-of-the-art models, which are again like 3 billion, like twice the size of this model, it was very competitive with that in the space. So finally, I'll end it up with a conclusion. So our framework shows that we are effective. Using this framework is effective in synthesizing more diverse and steerable conversational systems, which could be used to enhance the capability of small language models. These framework also achieve competitive results related compared to the models which are trained on human-annotated data sets, thereby addressing the limitations we have on good quality data set. For future research, we could focus on expanding CoDi's application to like other domains. We have focused on conversational grounded for now, improving the quality or exploring other cross-lingual capabilities. And finally, investigating in more sophisticated linguistic features or adapting it for specific user interactions. That is what I had for today. Thank you so much for being a great audience.